Hello everyone, I'm Ishan, and here I will talk about TCLR, Temporal Contrastive Learning for Video Representation. So this work was done with Rohit Gupta, Mumshad Rizvi, and Dr. Mubarak Shah. Yeah, so here is the overview of the presentation. So first I will talk about motivation for self-supervised learning in video, then instance contrastive self-supervised learning for videos, then inspiration behind TCLR framework, and TCLR framework itself, method, experiments, and analysis. So in this slide, I'll talk about the motivation for self-supervised learning in video domain. So we know that 3D CNNs can learn spatiotemporal features and outperform 2D CNNs, but 3D CNNs are data hungry. So most of the development done in the video understanding tasks are due to the pre-trained weights from larger datasets. For instance, if we consider a UCF 101 training from scratch with RGB modality, then standard models gives us around 60% of one accuracy. Even state-of-the-art architectures with lot of fancy data augmentation gives us 70% of one accuracy. But if we take a pre-trained weights from Kinetics 400, then it gives us 96% accuracy, which is huge jump from this scratch 60%. So this shows us importance of pre-trained weights in video domain. But we know that annotating a video is very costly compared to annotating an image. For an example, Kinetics 400 has 28 days of data, but we have like lot of unlabeled data from web content. So a feasible solution can be learning from unlabeled data. So in recent couple of years, contrastive self-supervised learning has been shown as an effective self-supervised learning technique. So here goal is to maximize agreement between different views of an image while maximizing disagreement between views of different images. So let's take an example of TCLR framework. So in TCLR framework, if we take two different augmented versions of an image and get their low dimensional projection, then goal is to maximize the agreement of the projection which come from the same image, whereas maximizing the disagreement between the projection which come from the different images. In this slide, I will talk about contrastive self-supervised learning in videos. So if we consider a TCLR framework and apply it naively for videos, then still it's an effective solution. So here we are doing instant discrimination by maximizing the agreement between clips of the same video. Let's try to understand from this figure. So if we take two clips out of this video one and randomly augment it and pass it through 3D CNN and MLP to this projection space, then the clips from the same videos are expected to attract, whereas clips from the different videos are expected to repel. Here is the equation for the instance contrastive loss, where the green term shows the positive for the anchor GI and red shows the negatives for the anchor GI. And H is the cosine similarity, and this one sign is the indicator function. So let's talk about the problem associated with the instance contrastive loss which we found. So it's a general practice in a standard video understanding task that we first divide the video into clip. We first take the clip level prediction and take their average to get a video level prediction. So, but in instance contrastive loss, since it attracts all the clips to a similar representation, it enforces the temporal invariance. So in this example of nearest neighbor retrieval, if we increase the number of clips per video, then instance contrastive loss gets a negligible boost out of it. Here it is like less than 5%. So it is the prime motivation for TCLR, where we explicitly increase the temporal diversity. So if in the case of TCLR, if we increase number of clips per video, then the performance goes significantly high. Here is a brief overview of the TCLR framework. Our goal is to encourage temporal diversity at two different temporal aggregation steps, that is clip level averaging and feature level pooling. So the first component is local to local temporal contrastive loss. Here goal is to enforce temporal diversity at clip level by contrasting clips from the same video. Let's look at the figure. From video VI, we first take 4 local clips out of it, and each of the clips is passed through 2 different random augmentation and passed through 3D CNN and MLP to get its projection into representation space. So after getting these representations, temporally aligned representations are considered as positive for contrastive loss, whereas temporally misaligned representation are considered as negative. And we sum it over all of the 4 temporal segments. So the second component is global to local temporal contrastive loss, which has goal of enforcing temporal diversity at feature level. So this slide has many new terms, so heads up. Let me start from this figure. So out of video VI, we first take a global clip with a higher skip rate and pass it through 3D CNN and gets its feature map. So instead of doing temporal pooling like we did before, we are taking each of the temporal slice and project it into the representation space through MLP. And we call it a local representation of the global clip. We are calling it local because it's a part of the feature map, it's not the full feature map. At the same time, we take 4 local clips out of the global clip and pass it through the same 3D CNN, and we do the temporal pooling and project it into the representation space. So after getting these representations, we consider a feature slice which is temporally aligned with the local clip as positive and the other local clips as negative. The same loss goes other way around as well. So here is the equation, and we sum it over all temporal segments. So one thing to note here is that we are not taking any negatives from this local representation to other local representation, or this global representation to any other global representation due to the conversion issue. Let's move to the experimental setting. So for tickler self-supervised pre-training, we do it on either on UCF 101 or Kinetics 400 videos without using any labels. So architecture tested here are 3D Resonate, R2+1T and C3D. So for downstream tasks, we are considering full fine-tuning of action recognition task, nearest neighbor retrieval, and fine-tuning with limited label data, and linear evaluation. So the first downstream task is action recognition. Here we fine-tune all layers after this self-supervised pre-training. You can see there are many recent papers in this domain. So the first protocol is doing the self-supervised pre-training on UCF 101 without using any labels, and then fine-tuning on UCF 101 itself. Second protocol is UCF 101 to HMDB, Kinetics to UCF 101, and Kinetics to HMDB. So our methods get significant boost over the state-of-the-art in all protocols. The second downstream task is nearest neighbor retrieval, where we check the representation quality without fine-tuning any layer. So for the top one recall, our method gets about 11% boost over state-of-the-art, and the similar finding holds for the other recalls. The third protocol is limited label classification, where our method gets the comparable performance to state-of-the-art with just using 10% of the data. So we do evaluation for each of the loss components on different protocols, and we find that each of the loss component is contributing to the final result. We also show that the learn temporal diversity through tickler. It helps in various downstream tasks through multiple clips inference. We also show that temporal diversity helps in distinguishing visually similar classes. So when we do IC pre-training, it doesn't get any huge benefit from over the scratch. Whereas in tickler pre-training, we clearly see the diagonal pattern of the confusion matrix. To summarize this talk, we propose 2 novel temporal contrastive losses. We got state-of-the-art over various video downstream tasks, and we showed that temporal diversity helps in video self-supervised learning. So if you have any questions, just reach me out on this email ID. We are about to put new results and link to the repository on our archive version. Thank you.